In this video, we are going to discuss Le Chatelier's principle. Le Chatelier was a French chemist and is the father of the equilibrium law. His work is now part of the fundamental understanding of equilibrium. Le Chatelier's principle controls the position of a chemical reaction. We will look at several factors and predict changes in equilibrium position. The first, change in concentration. The second, temperature change. And thirdly, pressure change. It is very, very important to remember in this section, only a change in temperature changes the equilibrium constant K. All the other changes that we talk about only change positions of the reactants and the products, but they do not change the constant. Le Chatelier's principle states that if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. In other words, the reaction will change the position of the substances to counter the stress of the condition. For example, if I compress a reaction, it will respond by shifting position to the side of the reaction that has the least amount of gas. It is very important to realize that although changes to the reaction may alter the equilibrium positions, they do not alter the equilibrium constant. Only temperature changes K, or Kp. Let's first look at changes in concentration. If a change in concentration happens, the reaction will shift to compensate for that change. For example, if the concentration of a reactant increases, the reaction shifts right to make more products. Equilibrium is restored, K remains constant. If the concentration of a reactant is reduced, the reaction shifts left to replace that reactant. Equilibrium is restored, K remains constant. Let's take a look at practice problem 13. You can follow along on page 622 in your textbook. Arsenic can be extracted from its ores by first reacting the ore with oxygen, called roasting, to form a solid As4O6, which is then reduced using carbon. As4O6 solid plus 6 carbon solid yields As4 gas and 6CO gas. Predict the direction of the shift of equilibrium in response to each of the following changes in concentration. Part A, the addition of carbon monoxide. Carbon monoxide is a product, so adding a product causes the reaction to shift left. B, the addition or removal of carbon or tetraarsenic hexaoxide. Carbon and tetraarsenic hexaoxide are both reactants, but they are also both solids. Solids are not included in the equilibrium expression and therefore have no effect. No shift takes place with the addition or the removal of these two substances. Part C, removal of gaseous arsenic. Gaseous arsenic is a product. If we remove arsenic, the reaction will shift right to replace it. Now we will look at pressure changes, and these are the things we need to pay attention to with a gaseous reaction. There are three ways to change pressure in a reaction. I can add or remove a gaseous reactant or product. 2, I could add an inert gas. And 3, change the volume of the container. There is one type of problem that is commonly given with respect to pressure in Le Chatelier's principle. Total pressure can change in a reaction by the adding of an inert gas. When an inert gas is added, the total pressure changes. But keep in mind the partial pressures of the gases that are reactants and products in the reaction do not change. Because of this, the reaction does not shift and remains unchanged. If a change in pressure happens, the reaction will shift to compensate for that change. For example, if pressure increases or if volume decreases, the reaction shifts towards the side with the smaller number of gas moles. Equilibrium is restored and K remains constant. If the pressure is reduced or the volume increases, the reaction shifts to the side of the reaction with the most gas moles. Equilibrium is then restored and K remains constant. An increase in pressure by adding a gaseous reactant or product will have the same results as a change in concentration. Now let's take a look at practice problem number 14. Predict a shift in equilibrium position that will occur for each of the following processes when the volume is reduced. Part A, the preparation of liquid phosphorus trichloride by the reaction P4 solid plus 6Cl2 gas yields 4 PCl3 liquid. If the volume is reduced, the reaction will shift to the side with the smallest volume and the least amount of gaseous moles. In this example, there are 6 moles of gas on the left side and no gases on the right. If we reduce the volume, this reaction will shift right to the side with the lower volume. Part B, the preparation of gaseous phosphorus pentachloride according to the equation PCl3 gas plus Cl2 gas yields PCl5 gas. In this reaction, we have 2 moles of gas in reactants and 1 mole of gas as a product. If the volume is reduced, the reaction will shift right to the side with the lower volume. Part C, the reaction of phosphorus trichloride with ammonia. PCl3 gas plus 3NH3 gas yields PNH2 gas plus 3HCl gas. In this reaction, there are 4 moles of gas on both sides of the reaction. Both sides will take up the same amount of volume, so reducing the volume of the overall reaction will have no effect. No shift takes place. Finally, we will look at changes in temperature. When temperature changes, energy is added or removed from the reaction. To determine shift, we need to know the heat of a reaction. Exothermic reactions that have a negative change in H move forward and increase their K at lower temperatures. Endothermic reactions with a positive change in H move forward and increase their K at a higher temperature. This should make sense. Endothermic reactions need energy to run, so the more energy that we give them, the more spontaneous they become. The reverse is true for an exothermic reaction, for the same reasons. You can also think of change in temperature as a shift due to the increase of reactants or products, just as we did with concentration. Just remember that energy is a reactant when the reaction is endothermic, and energy is a product in an exothermic reaction. Let's do our last practice problem. For each of the following reactions, predict how the value of K changes as the temperature is increased. Part A, N2 gas plus O2 gas yields 2NO gas. Change in enthalpy is a positive 181 kilojoules. This reaction is endothermic. Therefore, energy is a reactant. If the temperature is increased, we are adding more reactants. This reaction will shift right, and the K will increase as more products are produced. Reaction B, 2SO2 gas plus O2 gas yields 2SO3 gas. Change in enthalpy is a negative 198 kilojoules. This reaction is exothermic. Therefore, energy is a product. If the temperature is increased, we are adding more products. The reaction will shift left and therefore lower the K. This concludes the equilibrium video series. I hope this has been helpful, but please remember to read the book with the sections that we've covered in the videos. Thanks.